So let's continue with more questions and doubts from HC Verma. So basically in all these questions, we will be focusing on application of work energy theorem. That is work done by external forces plus work done by non-conservative forces equals to the change in kinetic energy plus change in potential energy for a system. And where we also know that delta U for a system is defined as negative of the work done by internal conservative forces. Okay, so, and of course we have seen the specific definitions of potential energy of a spring being half kx square, and the change in gravitational potential energy being mg into delta y, where delta y is the vertical displacement or the vertical component of displacement for a body of mass m under acceleration due to gravity equal to small g. Okay, so with these basic ideas in mind, let us look at more example questions from HC Verma. So in the last session, we have discussed somewhere up to question number 19 or so. Okay. So let's move ahead and discuss question number 21 next. So just go through question number 21's language. I'll put it up on the board and try to figure out how we can use work energy to solve it over here. So what the question is saying is that a projectile is fired from the top of a 40-meter cliff. Okay, 40-meter high cliff with an initial speed of 50 meters per second, but at an unknown angle, and we have to find the speed of the projectile when it hits the ground. So the situation is something like this. So let's say at a height like this of 40 meters above the ground level, we have fired a projectile at its initial speed of 50 meters per second. But this angle is unknown to us. Okay, so now the projectile takes this parabolic path and then eventually hits the ground with some speed v over here. So we want to find the speed v. Okay. So you can do this by kinematics also, but here we would prefer to do it by application of work energy theorem. So if you take the particle, so if you take the particle plus the earth as a system, you can see that as it is moving, there is only one force acting on it, which is conservative force of mg. So there is no external force doing any work on it. There is no non-conservative force doing work on it. So the change in kinetic energy plus the change in gravitational potential energy should be zero. So mechanical energy should be conserved. Yeah, so let's say the particle's mass is m. assuming mass m, you can see that A to B, the change in kinetic energy plus change in gravitational potential energy should be zero. So half m v square minus u square minus mgh should be zero. So you get a very simple relation that v is square root of u square plus 2gh. So now just substitute the values. So approximately this will come out to be 57.4 meters per second. Okay, so hope this is clear. Next, we'll do question number 24. So just go through it. Okay, so question 24 says that water pump lifts water from a level of 10 meters below the ground, and water is pumped at a rate of 30 kgs per minute. Okay. So a pump raises water at a rate of 30 kilograms per minute through a height of 10 meters. At negligible velocity. So find the power delivered by the pump. Okay. And we have to calculate the power delivered in horsepowers. Remember, 1 horsepower or British horsepower is equivalent to 746 joules. 746 watts. Okay, anyhow, so suppose a mass delta m of water is lifted through a height h at a speed tending to 0. The work done is this much. So the power is the rate of work done with respect to time. So that will be this much. So this 30 kilograms per minute, this is the rate of mass per unit time. Zero 0.5 kgs per second. Okay. So this will become 0.5 kg per second into 10 meters per second square into 10 meters. This is the height through which it's climbing. Okay. So this will give us the power in joules per second or watts. So 50 watts. So that is 50 divided by 746 horsepowers or British horsepowers. So pretty simple question. Questions related to power are generally simple like this. Just note down this question. Next, we will do question number 31. So horsepower or British horsepower, that's one and the same thing. 1 joule is rather 1 horsepower is equivalent to 746 joules per second. Okay. Next, we will solve question number 31. After that, we'll come to question 34 also. Just try this out first. Okay, so let's understand question 31. So we have this system of two blocks. And there's also a system of pulley involved. So this is the initial state of our system. And this block A has a mass of 4 kg, B has a mass of 1 kg. And initially the system is released from rest. And this is a frictionless surface. Oh, sorry, this is not a frictionless surface. This has a coefficient of friction, which we have to find out. Okay, so what the question is telling us here, Krish, I will come back to your question. And Diti, I'll discuss 32 and 36 also. Now, what this is saying is that after some time, the block B has come down through a distance okay. The 1 kg block is found to have descended through 1 meter and developed a speed of 0.3 meters per second. So during that time, A would have made a displacement of, now you can understand that constraint relation. This will pull 2 meters worth of thread. So A's displacement will become 2 meters. Displacement of A will be twice of displacement of B from constraint relation. And therefore, velocity of A will also be in magnitude twice of velocity of B. So this would have become 0.6 meters per second. So now if we take the block A plus B plus Earth as a system, then we can say that work done by friction is equal to change in kinetic energy of A plus change in kinetic energy of B plus change in gravitational potential energy for the block B. Okay, so from the diagram we can understand now that the work done by friction will be minus of friction into displacement of A. That should be equal to half mv square for A plus half mv square for B. Okay, minus this quantity because B is coming down, so its potential energy is decreasing. So let's substitute the values here. So minus mu mg, that is the magnitude of friction on A. This will be the work done by friction. So 4 into 0.6 square plus half one kg multiplied by 0.3 squared, minus 1 into 10 into 1. That should be equal to minus mu into 4 into 10 into the displacement, which is 2 meters. So this should be equal to 80 mu should become 10 minus 0.72 minus 0.045. So from this we'll get the value of the coefficient of kinetic friction. Okay. So this is how we can approach this question using work energy. Yeah, now Krish, your question is 1 kilogram watt is how many newtons? No, there's no relation like this because see, 1 kilogram watt is basically now 1 watt is 1 joule per second. So that is nothing but 1 Newton meter per second. So 1 kg watt is basically equal to 1 kilogram into Newton meter per second. So maybe you are confusing some other unit. I'm not sure, Krish. Okay. No, then there must have been some misprint. Tension cannot be in kg watts. Tension has to be given in newtons or dynes. Just send me a screenshot of the question later, Krish. Okay, I'll sort it out for you. Let's come to question 32 next. Diti has asked the question 32, so let's discuss it. So a block of mass 100 grams is moved with a speed of 5 meters per second at the highest point in a circular tube. So we have this kind of a situation. So we have a circular tube like this. Okay. So this circular tube is of radius 10 centimeters, and an object over here like this of mass 0.1 kg or 100 grams is at the topmost point, moving with a speed of 5 meters per second. Okay. And gravity is like this. This is a vertical plane. Now this all surface we have to assume is rough. So what will happen is it will come sliding down, but as it comes sliding down, friction is causing it to lose energy. So it might go up to here, then stop somewhere here, then come back sliding. And by repeating this many times, eventually going back and forth like this, it's coming to rest at the position B. So we have to find the net work done by friction. So the net work done by friction, you can see over here, will become the change in mechanical energy. Okay, so understood the point, Aditi. The inner surface is rough, so that's why what happens is that the particle will come sliding down, but it will lose energy because of the work done by friction. So as the particle is, moving with a speed v somewhere here at some point of time, there is friction acting like this on it, whereas normal reaction acts like this. You can see that mg is the conservative force. Okay, friction is the non-conservative force. And normal reaction acts in such a way that work done by normal reaction will be zero, because n dot ds is zero at all points. But the non-conservative force friction, this will do negative work. So this only is equal to the change in kinetic energy plus change in gravitational potential energy. This will be the work energy theorem for the statement. Okay. So from A to B, you can see the total work done by friction will become minus half mv naught square minus mgh, where h is this total height and this speed is v naught. So this will be the net work done. This is the question clear? Okay. Next, we'll discuss question number 34. Okay, so question 34 is very simple case because it's to do with a frictionless inclined plane surface. You just follow the instructions of the question for each part and work it out. Anyway, so there is this inclined plane of the angle is not given to us, but now there's a particle of mass 200 grams. Yeah, is kept at the top of the frictionless inclined plane, which is 10 meters long and 3.2 meters high. So this height is given to us as 3.2 meters, and this length is given to us as 10 meters. Okay. Now the first part asked is to lift the block from ground and put it at the top. What is the work done? The work done by the external agent to lift the block from the ground to the top. So basically this is the ground level, let's say. From here to here, work done by the external agent will be change in the gravitational potential energy. Okay, because it's at rest over here also when you place it. Whereas initially also on the ground it was at rest. So you're not changing the kinetic energy, only changing the potential energy. So that is 0.2 into 10 into 3.2. These many joules. Now the second part of the same question is asking that to slide the block up the incline, how much work has to be done? So the same thing, you'll see whether you directly lift it up and place it like this, or you slide it up. Okay, this was for part 1. This is for part 2. Okay. That will also be nothing but the change in gravitational potential energy. So it will be same because normal reaction is not doing any work and friction is not there. Understood the point, Tej? Why answer of part 1 and part 2 should be the same? Okay. Then third part, if it falls off the incline and drops vertically on the ground, what will be the speed when it reaches the ground? So if it falls off and comes vertically on the ground like this, then it will hit the ground with a velocity of, you can use kinematics or you can use work energy. So either way you can see that B will be equal to root 2 GH. Whereas in the fourth part, if it is sliding down the inclined plane, so by the time it reaches the bottom, it will have some speed V. Now here also you can use that same concept. Normal reaction is not doing any work, and mg is a conservative force. Okay. So if you use work energy theorem, you still have change in kinetic energy plus change in gravitational potential energy is zero, because work done by normal reaction is zero. So it's the same speed, only the direction of motion is different. Or you can also use kinematics. Okay. This time when you use kinematics, your acceleration will be g sine theta. Okay. So you can see that v is equal to square root of 2as. And here now we can see that h by s, so square root of 2gs sine theta is the same thing as square root of 2gh. So whether you go with the kinematics method or you go by the work energy method, ultimately you will get one and the same thing, and that answer should be root 2gh. Okay, good. Now next up we will discuss question number 36. So go through that and try it out. If you haven't done question 36 before, haven't tried it out, please go through it. We'll discuss that next. Okay, anybody got the answer for 36th question? So we have this kind of irregular track. And this section just at the end here is horizontal almost. So this is 1 meter high. And here this is 0.5 meters high, sorry, not 0.2. Okay. And then we release this particle from rest over here. So it comes down, it has maximum speed by the time it reaches here. Okay. Then again it decelerates. And by the time it comes here, let's say it has some speed v0. So if we directly apply work energy theorem from A to B, this is a smooth surface, of course. So you can see that while this particle is sliding down this inclined plane or sliding up the inclined plane, whatever be the case, at any instant, the normal reaction acting on it is going to be perpendicular to the instantaneous displacement, because the instantaneous displacement is going to be along the velocity vector. So this angle is 90. So the work done by normal reaction will always be zero at any instant, whereas mg is the conservative force. So friction is absent and work done by normal reaction is zero, because n dot ds is equal to zero at all points. So that is why change in kinetic energy plus change in gravitational potential energy is zero. That is, mechanical energy is conserved. Okay. So A to B, when we apply conservation of mechanical energy, we have half mv naught square plus mg into, now this will become minus of h1 minus h2. Okay, because you can see that the change in vertical coordinate from A to B is h2 minus h1. So that's actually a negative quantity. It's minus of 0.5 meters. So half mv naught square is equal to mg into h1 minus h2. So v naught is equal to root 2 g of this much. Okay. So that gives us the value of v naught. And now from here it's going into projectile motion. We want to find out this range. Yes, Tej. How will we find the range, tell me? No, see, the thing is the change in vertical coordinate, A to B. So it's the y coordinate at B minus the y coordinate at A. So it is h2 minus h1, which is the same thing as minus of h1 minus h2. So that's why here delta u has been substituted as this. This minus sign is there now for that. Okay, anyway, so we are getting the V naught as square root of 2 into 10 into 0.5. So root 10 meters per second. Okay. No, not that formula. How can you use that formula for range? That is for a projectile which is projected from the ground. This formula for range that you're talking about, that is for this kind of situation. It's not projected from an elevation point. It's not the case here. No? It's not happening here. So यहाँ पे क्या करेंगे? We'll say that okay, let's say this starts at t equal to 0 from here, and it hits the ground at some time t. So half gt square should be equal to h2. This is the y component of displacement, and along the x-axis r should be equal to that horizontal velocity v naught into time. So this is what we will use for the projectile motion part. Okay. So substitute in this. Okay. So the time of flight is 1 by root 10 seconds. Okay. So the range will become root 10 into 1 by root 10. That's why the range will be 1 meter. Okay. So while work energy is helping you to find V naught, but to find the range, you have to use the projectile motion concept over here. Work energy is not going to give you the range. You have to use the equation of projectile motion for horizontal projection from a height. This is the method that we use. Please let me know if there's any doubt about how the projectile motion part was solved. Okay. Basically using this concept that from a height h, if you project something horizontally at a speed u, how do we calculate the range? We calculate it using time. Okay. If you take this as your y-axis and this as your x-axis, okay. So from this we calculate the range. Okay, very good. Okay, next up, very important question. We'll do 39. So I'll explain the question. 38 also okay. So we'll do both the questions. They are actually interrelated. We'll do both of them. Okay, Krish, I'll finish writing this down. We'll come back to 38 and 39. Okay. Okay, so let's come to 38th. So you have a situation like this. On a tabletop, you have a uniform chain of mass m and length L which hangs with 2/3 part on the table. So let's say my chain is represented by this such that 2/3 of it is on the table and 1/3 part is overhanging from the edge like this. So this is L by 3. So, so this is a chain length L like this. So this is the initial state. Okay. Now from here, you want to lift it and place it on the table completely. So my final state, just a second guys. Okay. Stop. Stay quiet. Yeah, so from here my final state is that we are lifting up the entire chain and putting it on the table. So now the entire chain is here. So this is my final state. So we have to find the work done by the external agent to take it from the initial state to the final state. So in both states, you can see that the chain was at rest. Here also the chain is at rest to start with, and here also it is at rest. So there is no change in kinetic energy, but there is change in gravitational potential energy. So how we'll calculate the change in gravitational potential energy? You see that let's divide the chain into this like this. Okay. So now this point A has come over here. This point B is here. This point C is here. Okay, so this is your 2L by 3 portion. This is your L by 3 portion. So you'll see that the change in potential energy of the section AB is 0 because it's at the same horizontal level. The vertical displacement of the section AB is 0. But the change in gravitational potential energy of the section BC, that is something positive because that has gone up. It's positive quantity. So how we'll find it out? So the section BC, its center of mass is here. Okay, so its center of mass is at the midpoint. So it is at L by 6 below this level. And now it has reached here. Of the chain, you can see the mass is m by 3 and the vertical displacement of the center of mass is how much? It is L by 6 upwards. because center of mass is at the midpoint. Okay, this is vertical displacement of BC section center of mass. Okay. So is this concept clear? So from this, delta U for the section BC will become mass into G into vertical displacement. Okay. So now you substitute this here. Yeah, Vashish, because the center of mass is not moving by L/3 ना बेटा. उसका center of mass कहाँ पे है? Chain के L/3 वाले section के midpoint पे है ना. So for change in gravitational potential energy, we have to consider where the center of mass has moved now. You understanding, beta? The center of mass is not at the lowest end, na? Yeah. So actually, if you see now, if you chop the section BC into small little parts, you know, like each link of the chain. So the links which are nearer the top, they are hardly having any displacement, vertical displacement. The links which are nearer the bottom, they are having displacements closer to L/3. But the one which is right at the center, that is having a displacement of L/6 upwards. And that is like the average displacement, because some of them are having less than that, some of them are having more than that. So that is how the concept of center of mass works out actually. Okay, now 39th question is, no, actually what we have done is we have taken the displacement of the center of mass. Okay. So the concept we are using here, Vashisht, is this, that suppose I have any arbitrary kind of shape of rigid body, okay, and I move this body from here via some kind of path to here. Okay. Now I want to find out what is the change in gravitational potential energy. So it will be the mass into G into delta Y of the center of mass. So if the center of mass was earlier over here, at the final position, after making this displacement, the center of mass has gone over here, let's say. So I'll have to calculate this thing. This will be the displacement of the center of mass. So then this will be the horizontal component of the displacement, and this will be the vertical component of the displacement. This will be my delta Y of the center of mass. This will be my delta X of the center of mass. This will be my displacement of the center of mass. So M is total mass of the body or the system, and delta Y, Cm, is the vertical component of the center of mass's displacement. COM or CM, whatever we call it, that is the center of mass. Yeah. So now basically what happens is that the center of mass, now you will study in that chapter called center of mass also later. You might have started that chapter also with Hemant sir, right? So center of mass is the symmetry point with respect to mass distribution. So therefore, delta y of the center of mass actually becomes average delta y for the mass distribution. So that is why that is where this formula comes from. So yes, in a sense, we are actually averaging out the y component of displacement for all the particles, but that we don't need to average out separately. We can understand that whatever the y component of the center of mass is displacement, that only will be the average value of y component of the mass displacement. You have started center of mass in the other track in physics or not yet? Okay, you will be starting soon. You must be doing circular motion now. Okay, so you will understand a little bit more about this when you study about center of mass in the next 2 weeks. You will get a better idea of this, but just remember this is one of the applications of center of mass, why we use the concept of center of mass. Yeah, system of particles, that only is in that the first part is center of mass. Okay. Position of center of mass is the first part of system of particles chapter. Okay. Now if you don't want to use center of mass, there's another way we can do this also. Okay, but that becomes a bit lengthy, but I'll explain also. Alternate method of calculating the change in potential energy is like this, that now I'm just concentrating on the part which is hanging vertically initially. So just for that part, we'll do the calculation, because the part which is on the table, its potential energy is not changing. So going from this state, with this state here, so if we now consider a small element which is at a distance y from the top, so consider a small section dy. So this section has a is like a particle, and it has a mass dm, which is lambda into dy, where lambda is mass per unit length of the entire chain, that is. So you have the entire chain here. So the entire chain has mass m and length l, but this section is of L by 3. Okay. Now this dm is now going here now in the final picture. So this particle is going through a y displacement like this from here to in the final state. Okay. So this particle is undergoing a change in potential energy of dm into g into y. This is the change in gravitational potential energy of a section dy of the chain of mass dm. Okay. So now you see this lambda is m by l. Okay. So now the total change in potential energy So delta u will be integration of du for all particles from B to C. So that is integration of dmg dy from B to C. Now dm from here is m by l dy. Okay. So substitute that here. Take the constants outside. So mg by l comes outside. Y dy. Now at the point B, the y is 0, and at the point C, y is L by 3. So we'll get mg by L, y square by 2, limit y equal to 0 to y equal to L by 3. So mg by L okay, you get the same answer. So this is our change in gravitational potential. So this is the alternate method where we avoid using center of mass definition and we directly use integration. But that's unnecessary because we have a uniform change, so it's very easy to define the position of the center of mass. Okay, so this is the alternate method. Using integration. Yeah, so Diti, you wanted to note down this part? Okay, finished with that now. Let's come to the integration result below. So hope this is done. Now a method of solving 39th question is going to be somewhat similar using integration. So in 39 question, the chain again overhangs with 2/3 part on the table, but this time the surface has friction, and the chain, instead of being pulled up, it starts actually slipping off. So let's assume what we are doing is we are releasing the chain from the initial position like this. So if we release the chain from this position, and let's assume there isn't enough friction to prevent it from slipping. So its initial speed is 0. 2/3 part is on the table, 1/3 part is like this. Chain of mass m and length L. But this surface now has friction. Okay. So by the time the chain has just about slipped off completely from the table, we have to find out the work done by friction. So by the time this is happening, the point A is reached here and the point C is here. So this is the initial state. This is the final state we are taking. We have to find the work done by friction. Okay, the coefficient of friction is mu. So now see what is happening here is that while the chain is slipping, the frictional force acting on it is variable. Okay, so that is the thing that makes this question both interesting but also tricky at the same time. So we cannot directly calculate work done by friction as minus mu mg into displacement. Okay, so let me explain how that's working out. So at some intermediate time, let us say that our chain is like this. Okay. So what has happened is that from our initial position, this is displaced by x. So this section's length now is this much. Okay. So you can see that the weight of this section is going to be some mass as a function of x, where that will be lambda into 2L by 3 minus x, where lambda is mass per unit length. Okay, so it is going to be 2m by 3 minus m by L into x. That is the mass of this section. So the normal reaction acting on this section will be equal to the weight. So the normal reaction will be like this. So the kinetic friction which is acting on it, that will be equal to mu n. So that's a function of x. So that will be this sort of function. So now during a small displacement, if this makes a further small displacement dx like this, the work done by friction during that small displacement will be minus of friction into dx. Okay, so this is the work done by friction. As the chain slips through a small displacement dx, as shown over here. Okay, so the total work done by friction will be integration of this. So there will be integration of minus mu mg, which we can take outside the integral because it's constant, into the initial state where x was 0 to the final state where x is 2L by 3. Okay. This will become our net work done by friction. Okay, so this is a bit of a complicated question in terms of integration application. So first of all, just make sure you understand the initial and final picture, then we'll come back to the integration application. Okay, so from here, at some intermediate time, when our system is like this, this end of the chain has gone down by x, and this end of the chain has moved by x to the right like this. So during that time, this is what friction is doing. Okay, students, we will conclude the lecture here today because I have an appointment. Next time we will continue with more questions in HC Verma. We will discuss the remaining questions from HC Verma and then come back to some additional concepts in work for energy also, the relationship between potential energy and internal conservative force. So we will discuss questions from HC Verma as well as a module in the next lecture. So another 2 lectures before we finally wind up work for energy. Okay, that's it for today. People, wish you all the best. Continue in HC Verma. You can now complete all the questions based on the concepts you have learned. Okay, that's it for today. People, wish you all the best.